Welcome, everyone! Today, we're diving into a classic high school senior level challenge, a complex numbers exercise from a back exam. We aren't just going to crunch numbers, we're going to master the art of geometric interpretation. By the end of this, you'll see exactly how algebra and geometry dance together on the complex plane. Let's get started!
Before we move forward with the video, don't forget to subscribe, give it a thumbs up, share it with others, and leave your thoughts in the comment section. Your support helps us grow and keep learning together.
Here is our roadmap for today. We have two fixed points, A and B, and a mapping function f that transforms a point M into M prime. We'll start by finding the unmoving invariant points, prove a powerful algebraic identity, and then use that identity to see how whole circles can transform into other circles. Finally, we'll walk through a full geometric construction. It's a comprehensive workout, so keep your eyes on the prize. Let's tackle question 1, finding the invariant points. What does invariant actually mean? Think of it like a mirror. The point is its own image. In math terms, the point M is the same as its transformed version, M prime, which means we simply set the complex number z equal to its image z prime. Our goal is to solve the equation z equals z prime and find those special fixed values. Time for some algebraic action. To solve z equals z minus 1 over z plus 1, our first move is to cross-multiply by z plus 1. Watch how the equation unfolds. Z times z plus 1 equals z minus 1. When we expand and simplify, the z terms on both sides cancel out perfectly, leaving us with the elegant result z squared equals negative 1. Now remember our golden rule in complex numbers. Negative 1 is just I squared. This is the key that unlocks the solution. And there we have it. Since z squared equals negative 1, our solutions are z equals I and z equals negative I. But what does this mean for our graph? These represent the points with coordinates 0, 1 and 0, negative 1 on the imaginary axis. On the complex plane, these two green dots are the only spots that stay exactly where they are after the function f is applied. They are the anchors of our transformation.
Before we move forward with the video, don't forget to subscribe, give it a thumbs up, share it with others, and leave your thoughts in the comment section. Your support helps us grow and keep learning together.
Now for question 2a, we need to prove a specific identity. Z prime minus 1 times z plus 1 equals negative 2. This looks a bit intimidating, but we have a solid plan. We'll start with the expression for z prime minus 1, substitute our function, and use the power of the common denominator to simplify everything down. It's all about careful manipulation. Follow the logic here. We start with z prime minus 1 and substitute the formula for z prime. By bringing the minus 1 over a common denominator of z plus 1, we get a fraction where the z terms in the numerator cancel out entirely, leaving just negative 2. One final cross multiplication by z plus 1, and presto! We've proven our target identity. This formula is going to be our most valuable tool for the rest of the problem. Why did we just spend all that time on algebra? Because every complex number relationship tells two stories, one about distances and one about angles. By applying the module, the absolute value, we find lengths and distances. By applying the argument, we find rotations and angles. Remember, a complex number is a package deal containing both a distance and a direction. Let's translate that algebra into distances. Taking the modulus of our proven identity gives us the product of two lengths equal to 2. Using our geometric trick, where the modulus of a difference is the distance between points, this reveals a beautiful truth. The distance from A to the image M' multiplied by the distance from B to the original M is always a constant 2. AM' times BM equals 2 every single time. Now, let's talk angles. Using argument rules, the sum of the angles of our two factors equals the argument of -2. Since -2 sits on the negative real axis, its angle is exactly pi. Geometrically, this means that if you look at the vectors from A to M' and B to M, the sum of their angles with the horizontal is always a straight angle. It's like a geometric balancing act. Let's bring it all together on the complex plane. We've discovered two invariant laws for this transformation. First, the product of the lengths AM and BM is always 2. Second, the sum of their orientations relative to the horizontal is always pi. No matter where M wanders, its image M' must move in perfect sync to satisfy these two geometric rules. Isn't that harmony amazing?
Before we move forward with the video, don't forget to subscribe, give it a thumbs up, share it with others, and leave your thoughts in the comment section. Your support helps us grow and keep learning together.
Let's do a quick reality check to make sure this makes physical sense. Look at our seesaw analogy for AM' times BM equals 2. If point M moves extremely close to point B, the distance BM shrinks towards 0. To keep that product equal to 2, the distance AM' has no choice but to explode toward infinity. This perfectly matches our original equation, where z approaching -1 causes a division by 0. Logic and geometry are perfectly aligned. Time for a quick recap of our first major takeaways. First, to find invariant points, always set z equal to z'. Second, when doing algebra, be a hawk about your signs. That's where the sneaky errors live. Third, always remember your translations. The modulus is for rulers and distance, while the argument is for compasses and angles. You're building a great foundation. Let's move on to question 3, transforming circles. We are asked to prove that if M travels on a big circle C centered at B with a radius of 2, its image M' must move on a smaller circle C'. Our secret weapon? The relationship we just found. AM' times BM equals 2. If we know the distance BM is always 2, then AM' must be 2 divided by 2, which is exactly 1. Look at the result. Because the distance between point A and point M' is constantly 1, M' is trapped on its own path. It must belong to a circle, C', with its center at point A and a radius of 1. As the blue dot M orbits point B, its red shadow M' orbits point A. This transformation has essentially shrunk and shifted the movement. Pure geometric elegance.
Before we move forward with the video, don't forget to subscribe, give it a thumbs up, share it with others, and leave your thoughts in the comment section. Your support helps us grow and keep learning together.
Now, let's shift focus to question 4a and work with a specific point, P. We need to find the exponential form of P plus 1. Think of this as a 3-step journey. Find the algebraic form, x plus iy, calculate the modulus, r, to get the how far, and calculate the argument, theta, to get the which direction. Let's walk through it. Step by step. First, p plus 1 simplifies beautifully to -1 plus I times square root of 3. Next, we find the modulus is exactly 2. For the angle, we look at our trig circle. A negative cosine and positive sine put us right in the second quadrant. Our angle is 2 pi over 3. Putting it all together, we get the exponential form, 2 times e to the power of I, 2 pi over 3. We've got our magnitude and our direction. In question 4b, we ask, does point P actually sit on our circle C? To prove it, we just need to measure the distance from P to the circle's center, B. That distance is the modulus of P plus 1. Wait a second, we just calculated that in the last step. The distance is 2, which exactly matches the radius of circle C. Confirmed, P is a member of circle C. Moving to question 4c, proving points are aligned. To show that A, P prime, and Q are on the same straight line, we use vectors. In the world of complex numbers, we calculate the ratio k of their differences. If k turns out to be a pure real number, no I involved, then those vectors are collinear and our points are perfectly lined up. If k is negative, they just point in opposite directions. Let's prep our coordinates for the final calculation. First, we find Q by using the conjugate of P, giving us 2 plus I times square root of 3. Next, we find P prime by applying our transformation function f to point P. After some standard complex division, multiplying by the conjugate to clear the denominator, we find that P prime is located at 1/2 minus I times square root of 3 over 2. Time for the grand finale of our alignment proof. We compute our ratio k. Notice how the denominator is exactly -1/2 times the numerator. They cancel out perfectly, leaving us with a final ratio of k equals -2. Since -2 is a real number, we have mathematically proven that points A, P prime, and Q are perfectly aligned on a single straight line. The algebra never lies.
Before we move forward with the video, don't forget to subscribe, give it a thumbs up, share it with others, and leave your thoughts in the comment section. Your support helps us grow and keep learning together.
Now, let's be geometric detectives for question 4D. How can we find exactly where P prime is without any more math? Let's use our clues. 1. P is on circle C. 2. That means P prime must be on circle C prime. 3. Q is easily plotted using symmetry. 4. Most importantly, A, P prime, and Q are on a single straight line. We have everything we need to draw it. Here is your construction guide. First, draw the two circles around A and B. Next, plot P and its symmetric counterpart, Q. Now, draw a straight line connecting Q and A. The magic moment happens right here. The intersection of that line and the smaller circle, C prime, is exactly where your point P prime is located. It's the perfect marriage of drawing and calculation. Let's do one last verification. Does our drawing match our math? Look at vectors AQ and AP prime. AQ goes up left, while AP prime goes down right. They are pointing in opposite directions. This is exactly what our ratio k equals -2 told us. Vector AQ equals -2 times vector AP prime. everything is perfectly consistent. Geometry is just algebra you can see. Fantastic work! You've successfully navigated a complex back exam exercise. Remember the big takeaways. Use modulus for circles and real ratios for alignment. Always draw a quick sketch to guide your thinking. It's like having a map for your algebra. Avoid mixing up your point order, and you'll be a complex numbers master in no time. Great job today!
Before we move forward with the video, don't forget to subscribe, give it a thumbs up, share it with others, and leave your thoughts in the comment section. Your support helps us grow and keep learning together.